The afternoon is free, but the common room at the math department will be open for those of you who want to work or use it. It will be open all the afternoon. So the last speaker of today is Kevin Pilgrim, and the title is right there. So thank you.
Can you hear me?
Yes.
Great. So it's a real privilege to be here in this wonderful facility in front of friends, very old friends, mentors. Thank you very much, all of you, for your collaboration, for your mentorship along the way. It's fantastic. This has always been such a great place to visit and develop. And I realize I'm standing between you and lunch. So I will try to keep things on the lighter side. There'll be no technical proofs or anything. Fundamentally, what I want to do is give a sort of sales pitch for a certain point of view related to the combinatorial theory of critically finite maps, which I'll define in a minute, and then develop in a bit more detail one aspect of this, which is mostly work due to Dylan Thurston that I had a small part in. Okay. So a critically finite map, here I'm talking about a holomorphic map from the Riemann sphere to the Riemann sphere, has 2D minus 2 critical points counted with multiplicity, and we say it's critically finite if each critical point is eventually periodic. And standard in the subject is to pay attention to this set, the forward orbits of critical points. So for me, that set will always be finite today. So what about some examples? Let's look at z squared plus I. The point at infinity is critical. It's fixed. 0 goes to I minus 1, goes to minus I, and then goes back to I minus 1. Another one is some rational function here. The critical points are at 2 and 0, with 2 mapping to 0 by degree 2, 0 going to infinity. It's a double pole by degree 2, infinity going to 1, and then that's a fixed point. So there are some simple examples of critically finite rational maps. And featured very prominently in Jeremy's talk just a second ago, the centers of the hyperbolic components of the Mandelbrot set are critically finite quadratic polynomials. And indeed, this density of hyperbolicity conjecture that he was presenting results on can be sort of phrased in the following way. If you take any interesting parameter C in the complex plane, and I'm not going to define interesting, or you could say infinitely renormalizable, for example, then that parameter is actually a limit of critically finite guys. So this is one reason to pay attention to such things. There are lots of other reasons to pay attention to critically finite maps. They explain matings in the quadratic family. They characterize laminations associated to polynomials. They allow one to take limits and look at maps with interesting and wild behavior. So in some ways, the theory of critically finite rational maps is their role is a little bit like the role of the rationals in the real numbers. So they're countable and you can get your hands on them, and by taking limits you hope to learn things about everything. So what has been called the fundamental theorem in complex dynamics is the following theorem, originally proved by William Thurston, and it appeared in ACTA 1993. It characterizes by combinatorial conditions the set of critically finite holomorphic maps among the much larger set of critically finite topological maps. And I'll give an example in just a sec. And then it also asserts a rigidity result that such guys are determined by their combinatorics. Okay, and don't say the word Lattice examples. Everything here is modulo state, flexible Lattice example. So there's just sort of standard disclaimer. It's the private. It's that fine print that you never read that comes with your credit card. And what I've struggled with for many, many years is trying to explain aspects of this theory to people not in complex dynamics. You have to define critically finite branch coverings, and you have to define combinatorial equivalence, and these things. And it's always been a little bit painful. So what I want to do is discuss another way of pitching this. Okay, so what do I mean by critically finite branch cover? Well, let me first define a Dane twist. So here's an annulus in the plane. There's a blue arc connecting it. And a Dane twist is a homeomorphism that's the identity on the boundary and that does something like this. So that's a Dane twist. And here's an interesting thing you can do. You can take the quadratic polynomial z squared plus I that we just looked at before. There's the origin. It goes to I minus 1 goes to minus I, and then there's a 2 cycle there. And let's take this green curve and think of it as the central core curve of this annulus over here. And let's do a Dane twist about that green curve. And post-composing z squared plus I by this thing gives an example of a critically finite branched covering of this sphere to the sphere. And it turns out that when you do that and you get a map G, then this red curve has the property that its inverse image, it's a nice exercise in taking the whole chalkboard and covering it with pictures to see that under G, the preimage of this red curve is actually homotopic to itself and maps by degree 1. And then there's some other preimage that is in essential or peripheral relative to this set of 3 dark points. So that red curve is an obstruction to the existence of a topological conjugacy to up to homotopy to a quadratic polynomial. Because if you put the Poincare metric on the complement of these 3 points and lifted that complex structure, which you suppose was invariant, and represented this red thing by a geodesic, well, when you lift, that's a local isometry. But then when you include, because you have this extra point that you would have to fill in, that inclusion is a contraction. And so the red curve would have length shorter than its geodesic representative, which is impossible. This is a sort of the flavor of Thurston's characterization that a critically finite branch covering is conjugate up to homotopy or up to isotopy, they're equivalent, when you don't have some sort of curve family that represents some kind of obstructions. Okay. So what was fascinating, and this problem was actually posed in Doherty and Hubbard's paper, is what kind of equivalence classes do you get when you twist z squared plus I, say by an arbitrary mapping class? And this was solved by Bartholdi and Nekrashevich some years ago. If you twist z squared plus I by some homeomorphism, then you might get one of 2 rational maps up to equivalence, but you could also get a 1-parameter family of obstructed examples. And in contrast, if you twist Doherty's rabbit, you only get 3 classes up to combinatorial equivalence, and they're all represented by rational functions. That's a consequence of a theorem of Bernstein and Levy. So this is sort of rich and varied behavior, even among the most simple examples. So what I would like to propose is a perspective that I'll call branched mapping class semigroups as a fruitful unifying idea. And this grew out of years of thinking about it and the results of Bartholdi and Nekrashevich and also Sarah Cook. And I would like to think that it shifts the discussion into a more natural context and connects it with many areas. So I'm going to breeze through in part 2 here very, very quickly since it's late, and then state some results along the way. And then towards the end, I'll focus on some new connections with one-dimensional real techniques. Okay. So what do I mean by a mapping class semigroup? So it's convenient to identify the Riemann sphere and the 2-sphere and P1 just once and for all. That way I get to call topological things by S2, and I get to call the Riemann sphere holomorphic things by the Riemann sphere. But the identification is fixed once and for all. Okay? And P is going to be a subset of the sphere, which is fixed once and for all, and should have at least 3 points. Okay, so in the theory of mapping class groups, what do? The objects that you're working with are homeomorphism. They're homeomorphisms, and then you mod out by some equivalence relation. And there, I think, is the beginning of how, in hindsight, some of this theory should have been developed in the first place. So the most primitive objects in the theory of mapping class groups are the homeomorphisms themselves. And if you're working with surfaces with marked points, you're fixing those marked points once and for all. And so let's look at homeomorphisms here. And I'll assume there are the identity on P. I didn't indicate that, but everything will be pure. Here's the identity component. And the mapping class group, the pure mapping class group, is just the quotient this, which is a countable, finitely generated group. Okay, so let's do the same thing for branch coverings. Okay, let's just look at the space of branch coverings from the two-sphere to the two-sphere that leave this set invariant and for which the critical values are contained in this subset. So by definition, this set, which typically consists of higher degree things, I'm on purpose throwing in the things of degree 1. And then it turns out, it's not so trivial, but it's true, that composition is well defined on homotopy classes. So you can look at this sort of double coset space where you pre and post compose by homeomorphisms homotopic to the identity, and composition becomes well defined. And this is then a countable semigroup. It contains the mapping class group, and it contains, and its elements are represented by the branch coverings of the type that we were discussing, like the twists of z squared plus I. Okay? But it has a bit of extra structure that's not present when you deal with mapping class groups, namely that there's a commuting action on the left and right, two commuting actions of the pure mapping class group. You can pre and post compose by homeomorphisms, and that's well defined on homotopy classes. And Bartholdi and Nekrashevich call this a biset structure. Okay, bi meaning two, and set, it's like a G action, but you have commuting actions on the left and on the right with some certain properties. Okay. Okay. So let's imagine that we're thinking about the theory of mapping class groups, and let's think about what some of the invariants are that you develop when you study mapping class groups. So let's suppose we have one of these guys in here, like a twist of z squared plus I. What can we do? Well, it's very natural to look at what happens on pi 1. So for surface homeomorphisms, whoops, did I skip one? No. Okay, so here's something you can do. You can take the sphere, you can puncture it at P, you can lift, and you get a covering space. And it's well known, right? The induced map on fundamental group is injective, so it'll have an inverse. Okay, that inverse isn't every well defined, but it's defined on a finite index subgroup. And then you can post-compose that by the inclusion of this smaller set into this set. And okay, it's only defined up to inner automorphisms, but so what? So this is an invariant that's called the virtual endomorphism on the fundamental group, and it's very naturally associated to F. And it's clearly an invariant of the homotopy class. Okay. So what else can you do? Well, then the notion of combinatorial equivalence becomes nothing more than being conjugate. Okay? So just as people ultimately are interested in questions like determining when two mapping classes are conjugate or solving the conjugacy problem, so too here our conjugacy class is nothing more than the diagonal orbits of this action of the pure mapping class group. Okay? And so where, in some sense, we went wrong at the beginning is, the rabbit and the airplane have different post-critical sets. And so we were focused on combinatorial equivalence because we need to be able to move that set around. But that destroys the algebraic structure. Okay, composition is not well defined on combinatorial classes. It's well defined on homotopy classes. Okay, so herein lies the advantage. When we rigidify things a little bit in this way, we get a more natural algebraic structures. Okay, so our very natural question then is, let's classify the conjugacy classes, just like one would do for mapping class groups. And then in the classical theory of branch covers, there's a notion of a Hurwitz space. You take a branch cover, you pre and post compose by homeomorphisms, but now it's not the diagonal action. So this is a weaker equivalence relation than conjugacy. So the set of all twists of a given element is called its Hurwitz class. And they all have the same degree. So that's another very natural thing we can look at. And then that Hurwitz class generates a semigroup under composition that we can call its Hurwitz semigroup. So the degrees are then unbounded. So these are all very natural objects associated with our setup. So there's an additional one, which in some sense is not a dynamical plane invariant. It's a parameter space invariant. there's a finite index subgroup of the mapping class group, which has the property that it lifts to a pure mapping class under F. And this gives something called a virtual endomorphism on the pure mapping class group. And this is a rich source of additional invariance that's intimately related to moduli spaces and so forth. So this is something extra that's present, not present when we study ordinary mapping classes. So you look for mapping classes that lift under F to a mapping class element. Okay? Everything's pure. Okay? And then you map H to H tilde, because if you have two guys with this property, you can push them to the other side, and you get a homomorphism. So there's a finite index subgroup of the pure mapping class group, which lifts, and then you get a canonically defined invariant associated to one of these critically finite branch maps. Did that answer your question? Okay. So, how in mapping class groups do you get started? The first theorem in the subject is the Baire-Nielsen theorem, and it says that if you take a mapping class and send it to the induced outer automorphism on the fundamental group, then that's injective. And if your surface is closed, that's actually an isomorphism. If your surface has punctures or marked points, there's a planarity condition you have to pay attention to that I've just buried here. So we know what the image is, but writing it down is technical. Okay? And the same theorem is true in our subject. So this guy, well, it's a surjective homomorphism from the fundamental group to itself. It's not defined everywhere. It's defined in a finite index subgroup, so that's the virtual part. It's defined only up to inner automorphisms. That's the outer part. They happen to be surjective, and they're endomorphisms because they're many to one. Okay. But the theorem is precisely the same. Okay. So this is the Baire-Nielsen theorem for critically finite branch coverings. Okay. What is a consequence of this, though? So we struggled for years with a data structure necessary to pin down something like a twist of z squared plus I. We just didn't have any way to tell a computer how to do this. But with this new algebraic perspective, we know how to do this. And Laurent Bartholdi has now a computer program. And if you want to tell it, so this is a degree 6 branch covering. It's fairly complicated, and it's more or less sort of randomly chosen. But this is now the input syntax to tell a computer what one of these objects is. And he's also implemented the iterative pullback algorithm on Teichmüller space, very much like the skinning map that Yair was talking about earlier. He's implemented this on computer, and if you're, if you want to find an example of a map with certain properties, and you have a combinatorial description of this map, you can read off this algebra, you can feed it into the computer, and it will draw you the Julia set. So this is output of Laurent's program. So I think this is a transformative moment in our subject, because we did not before have this flexibility of describing in a more or less arbitrary fashion the combinatorics of something and then seeing if there exists a corresponding rational function. And we can now do that. Okay. In mapping class groups, it's well known that the mapping class group is the fundamental group of moduli space. Okay? So what is the setup in our context? Okay? So here I'm using the fact that S2 and the Riemann sphere are identified. So I really mean equals there. So there's a canonical map from here to here by taking traces of homotopies. And there's a map going the other way, which is isotopy extension. And so this really is an equality because I've identified things in this way. Okay, and this symbol will denote the constant motion of the set P in the Riemann sphere, regarded as an element of this fundamental group. So it's just the trivial constant path. What is a corresponding setup for our branch mapping classes? So this is the idea of Sarah Cook. She associates to this Hurwitz space that we were just talking about before the following diagram. So here's the universal cover of moduli space. The domain of that virtual endomorphism on the mapping class group is a finite index subgroup of the mapping class group. And you can take the quotient of Teichmüller space by that. And this, you got a space W, which is associated. There should be a subscript H there, okay, depending on the Hurwitz class. So this is a finite cover. And then there's also an induced map that goes this way, which is essentially coming from erasing preimages of extra points when you lift complex structures. So this diagram is associated canonically to the Hurwitz class. Okay? So what is, in this setup, an element of our homotopy classes of branch mapping classes? Well, here's what you do. You take your base point down here, and there are some finite number d preimages under this map. You label those 1 through d. You push them down here. Now you have, say, d labels down here. And for each one of those labels, you pick a path from the base point to that label and record the homotopy class of that path. And that is an element of this branched mapping class group, as one can check. So there's a concrete interpretation of these elements as not loops this time, but paths in moduli space. So a lot of attention has been focused on if somebody gives you a concrete example of a map and you want to know is it equivalent to a rational map, you have to work very hard to rule out all these obstructions, and you worry about there being infinitely many things to check. So here's a far easier thing. Instead of asking whether f itself is obstructed, let's ask whether there exists some guy in this Hurwitz class that's obstructed. So this is a much weaker question. Okay? And that turns out to be kind of interesting. So a generalization of this Bernstein-Levy theorem is that this Hurwitz semigroup consists entirely of rational functions. So that will be the case for topological polynomials, all of whose critical points fall into cycles containing critical points. So if you're in that setup, then this hypothesis will actually be true by Bernstein-Levy. That's equivalent to the existence of a non-empty compact set, which is invariant under this correspondence that I wrote before. So I'm regarding this as a holomorphic correspondence on moduli space. This is a finite cover. This is a holomorphic map. And so going from here to here this way gives a holomorphic correspondence on moduli space. Okay? And you can check that condition by the following object. You make a directed weighted graph whose vertices are mapping class orbits of multicurves. And then if you take a multicurve, there's a function on it which sends a multicurve to its preimage if for some f. So you make a whole bunch of edges. So if there exists an f within the Hurwitz class with the property that such a multicurve pulls back, then you join it by an edge. And you take all such things. And then you weight them by these so-called Thurston linear transformations. And you look for cycles in this. And if you find cycles where taking the product of the weights along the cycles, that would give a square matrix. And that square matrix would be the Thurston linear matrix associated to a composition of twists of elements of your Hurwitz class. And if you find obstructions there, then you will find obstructions in your Hurwitz class. So this is a generalization of this Bernstein-Levy theorem. So let's see this. I'll show you an example in a moment. But what's tantalizing is that this graph seems to capture the end behavior of this correspondence on moduli space. And if the cardinality of P is 4, moduli space is a triply punctured sphere, and you can use complex analysis and power series expansions near the cusps, and you can work out what everything is. And so we have some partial results with Sarah and Nikita just to be published this year. But in higher degrees, I don't exactly know how to formulate this. So that's one reason why I wanted to mention this. So here's an example of z squared plus I. Okay? So up to the action of the pure mapping class group on the sphere with 4 points, there's 1 point, 2 points, 3 points, and the fourth point at infinity. There are 3 orbits of curves: the green curve, the blue curve, and the red curve. Okay? Just looking at set theory, so not paying attention to the precise formula for z squared plus I, so the same thing will be true for any twist of z squared plus I. If you have a blue curve, okay, and you notice the inside of the blue curve omits this point, so the preimage of the, and it also surrounds the critical value at I. So the preimage of this blue curve has to avoid all the preimages of this point. But there are two preimages of this point and this point. So all the preimages of this blue curve have to be peripheral. And so you take a blue dot for that one, and you send it to a black dot corresponding to a peripheral curve. And then you weight set that, say, by 1/2, because it'll have to unwind by degree 2. And then a similar analysis, you realize that this green curve surrounds the critical value here. It avoids this point, so its preimage has to avoid this point. And you realize that a curve of color green has to pull back to a curve of color red. And a curve of color red has two choices. It could have a preimage which is, again, of color red. Might not be exactly the same curve, okay, but it would have to surround these 2 points in a similar fashion. Or it could become the green one. So you write down a little diagram like this. And it turns out the inverse of that holomorphic correspondence is this rational function, which was an example I gave you earlier, up to conjugacy. And notice that as you go backwards here and take reciprocals, you see 2, 2, 1, 1, and that's exactly 2, 2, 1, 1. So there's some sort of magic going on between the behavior of curves in the dynamical plane and the end behavior of these correspondences on moduli space. And I think I have developing an understanding for that when the cardinality p is equal to 4, but in general, I don't know. There's a huge family of examples called nearly Euclidean maps that we investigated in an earlier paper called nearly Euclidean maps. I'll just breeze through this. Here, ignoring the green arrows for the moment, is a topological description of the lattice example of degree 4 that featured so prominently in Laura's talk. So the target, the codomain, is a sphere, which I think of as a double of Euclidean square with a white face and a black face. The domain is, again, a double of a square drawn here. So you take this part and you fold it over. So now I have two spheres. And the map z goes to 2z on a complex torus descends to a degree 4 map on the sphere. And it simply affects a kind of subdivision rule where each face is subdivided into 4. So I take that guy. That's a critically finite exceptional rational map. And I post-compose it with a push homeomorphism that sends that corner to that point and that corner to that point. And the arrows have to be green. The theory of mapping class groups has yellow arcs, apparently, in FLP that feature so prominently. And here they have to be green. This is a critically finite branch map. And there are algorithms for computing with this guy and its generalizations, nearly Euclidean maps. And so I just, this is the input syntax for a program written by Walter Perry. And there, every Thurston multiplier is less than 1. And the conclusion is that every map in this Hurwitz class is rational. So we're at a stage where we can do systematic experimentation on large families of examples. Okay. All right. So I'll now transition a little bit to some other work. Again, most of the ideas due to Dylan Thurston. So what's the motivation? For mapping class elements, the existence of an invariant train track, and I'll sort of say what that is in just a sec, it's an embedded graph with certain invariance properties with weights on edges, implies the existence of an optimal geometric representative, which is a pseudo-Anosov map. And that's a positive criteria. Thurston's theorem, the fundamental theorem, is a negative criterion. It says if you don't find obstructions, then you are rational. But it doesn't say if you do have something, then you are rational. It doesn't say that. And a train track is a positive criteria. If you have an invariant train track, then you get this beautiful geometric representative of your surface homeomorphism, which stretches along leaves of a quadratic differential. Okay. So what is a train track? Well, it's a kind of limit of something like this. So here there's a homeomorphism which makes these 2 points do a do-si-do and makes those 2 points do a do-si-do. You compose one with the other. And you take a curve and you look at many, 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 many iterates. And then this curve starts to become organized into sort of strands. And so you collapse the strands and keep track of the relative numbers of strands in each sort of branch, and that's an invariant train track for a surface homeomorphism. Okay? I'm sorry? What is that picture?
Stars in the sky?
Yeah, I stole it from the memorial conference for William Thurston last year.
This is a picture from the wall of the math department.
Maybe they superimposed it with the new background, or I didn't know how this was drawn.
I can tell you, I made it.
Okay.
Yeah, it's Thurston's image from the wall of the Berkeley math department superimposed over his background. Sorry?
Thurston did. It was a DS and BT.
Thurston and Sullivan, I think.
So I'm not going to define train tracks formally, but I just want to give a sort of flavor. You take something like this, and you're going to collapse these strands, and then you're going to weight the strands by the relative number of, or weight the branches by the relative number of strands. And then that resulting graph will be invariant in a certain way. And then conversely, if you have a surface homeomorphism that leaves invariant, a train track that sort of fills most of the surface, then you can construct a very nice geometric representative of this. So our goal was to find a similar criteria for equivalence to a rational map. So, okay. We're going to restrict to a subclass of rational maps, namely ones which are hyperbolic. So I want each cycle in our post-critical set to contain a critical point. So here's an example, 1 minus 1 over z squared. So it's a double pole here. It goes to infinity, which then goes to 1, which then goes to 0. So there's its Julia set. So Jeremy already mentioned polynomial-like maps. Well, a rational-like map is something that's constructed in almost exactly the same way. So here is a neighborhood V where I remove small neighborhoods of the attractor. So the attractor was at 0, 1, and infinity. So I'm removing this disk, that disk, and then the complement out here to get this, the three-hold sphere V. And then I take an inverse image of that. Well, this thing shrinks a little bit, this thing shrinks a little bit, this thing shrinks a little bit. So I also get a hole here, so I get a 4-hold sphere. So in this setting, U is a 4-hold sphere, V is a 3-hold sphere. The closure of U is contained in V, and I have an unramified cover, holomorphic, from U to V. Okay, so this is a rational-like map. Jeremy talked about polynomial-like maps, but here this is a rational-like map. Okay. So there's a connection between such rational-like maps and critically finite hyperbolic rational maps. Namely, if you have a rational-like map where you haven't re-embedded U inside V in a strange way, so strictly speaking, you want it to be surjective on pi 1, then you can use QC surgery to extend this rational-like map to a critically finite hyperbolic map. Basically, you just fill in the holes and map the disks where the holes used to be by some powers of z. So if the boundary of the hole maps by degree 2, you sort of glue in a copy of z squared. And there's a most excellent book on the subject that tells you how to do this. So let's suppose now we just have a topological guy where each cycle of P contains a critical point. So it's a candidate to be equivalent to a hyperbolic rational map. I'd like to find a rational-like map that's somehow associated to this thing. That's sort of ambitious, so let's try to find a one-dimensional real cartoon for such a thing. So a spine for the complement of the post-critical set is just a finite graph onto which this punctured sphere retracts. Okay? So we're supposed to capture all the topology. Okay? Then let's take a pre-image of that under F, and then the inclusion of the two-sphere minus this bigger set into S2 minus the post-critical set. That inclusion then gives a map from this graph onto the downstairs one. Okay? And that sort of pair up to some natural notion of equivalence actually determines the homotopy class of of f. Okay, so I can throw away all the, the details of f and just record this kind of pair and some planarity conditions, and now I know f. So I have a one-dimensional cartoon for this. So the Hubbard trees that Jeremy was talking about are a kind of version of this, adapted for certain kinds of polynomials. So the intuition is to try to put numbers on the edges of the spine and then think of those numbers as lengths of rectangles. We formulate this in a slightly different way because we have lots and lots of geometric quantities associated to these. So for consistency with what Dylan has written, we're going to call an assignment of positive numbers to the edges of gamma a length measure. And then gamma together with those, we're going to call an elastic structure. Okay? So it's nothing more than I have a finite graph. It's sitting inside the sphere, and I put, you can think of it as a length. You just put a number on each edge. So each edge is an isometric to a Euclidean interval of some length, and that's an elastic structure. And then in the setup that we just had, where we had a graph gamma 1 and another graph gamma 0, and we have a homotopy class of map from gamma 1 to gamma 0, anytime we have two elastic graphs, there's a number called its embedding energy. So I take and maybe I'll just use the board briefly. So here is an edge in gamma 0, and I take a point, and here is some continuous map C, and I should think of this as that inclusion. And there may be a variety of strands over this guy, so there may be many points that map. So here's, here's a 1x1, here's another x1. There may be more than 1 point. And, well, I'm assuming that this map is, say, Lipschitz or something, so it has a derivative. And I take the derivative here and the derivative here, and I add up those numbers. I get a number that depends on y. I let y move around, and I take the soup of all of those. This is a quantity called the embedding energy. Okay. And then here is our positive criteria for rationality. This is Dylan's theorem. Okay? So a critically finite branch covering of hyperbolic type is equivalent to a rational map if and only if you can find a spine and length structures on the edges, that is an elastic spine, okay? And some iterate such that if you pull back n times and take that graph and then include it back into the original one, then that embedding energy is less than 1. Okay, so this is a positive one-dimensional criteria. Okay, if you can, and I'll give an example with some color pictures in just a sec.
The embedding energy, did the elastic structure appear in your formula for the embedding energy?
Yes, because you need, in order to calculate the derivative, you need to know the lengths, right? Because the derivative will be an asymptotic stretch, for lengths. And so,
can you go back one slide? Sure.
Yeah. Sure. So here, right here, it's implicit in the definition of this absolute value sign. Okay. You can't make sense of the norm of a derivative without a metric on the source and target. So here's a metric on the source. There's a metric on the target. And there's a ratio. Okay? Think of C as just piecewise linear. So then there's just a slope at every point, and then you're just summing up the slopes.
Okay.
Yeah. Okay.
Back to the theorem?
Oh yeah. Okay. Okay. So maybe let me show you an example.
Homotopy have to preserve somehow the length that you put on the graph, or?
No, it doesn't.
I mean, but then you can just, put the length of, if you can put an arbitrary length of gamma n, then you can, just. Oh,
I'm sorry. Yeah, no, I didn't. So here, you have to lift the structure downstairs to one upstairs. The tilde shouldn't be there. So you're going to metrize this guy on the bottom, and then you're going to lift it, and now you have I should just, I think, show an example.
Okay.
So let's. So, whoops. Yeah. Okay. Yeah. So how does this work? So let's do this for 1 minus 1 over z squared. Okay, the post-critical set in that example has 3 points. So the negative criterion is vacuously satisfied. It's equivalent to a rational function. We know that. Of course, we have a formula too. But let's see how that works in this context. Okay. So this is supposed to be the same thing as this down here. Okay. So the post-critical set was 0, 1, and infinity. And so this union of blue, red, and green, okay, that's this blue, this red, this green. Okay, A is going to be 0, B is going to be 1. That is a spine for the complement of the post-critical set. Okay, so if I puncture the sphere at 0, at 1, and at infinity, everything retracts onto this picture. Okay. And we're going to assign the blue guy to have length 2, the red guy to have length 1, and the green guy to have length squared of 2. Okay. So that is an elastic structure on the spine downstairs. Okay. When I lift under 1 minus 1 over z squared, okay, so I'm going to just take this picture downstairs in the dynamical plane and just lift it. Okay, I didn't draw that. But the graph that you get looks like this. There'll be 2 copies of the red edge, there and there, and they have length 1. There'll be 2 copies of the green edge, there and there. They have length root 2. And there's 2 copies of the blue edge, there and there, and they have length 2. But what we have is an inclusion. Okay, so there is negative 1. That's 0. That's 1. We have an inclusion of this punctured sphere, 4 times punctured sphere, into the 3 times punctured sphere. And so that retraction has to collapse these 2 things onto gamma. So the inclusion of the sphere minus 4 points into the sphere minus 3 points, that retraction, composing that with the retraction onto the spine is going to give a continuous map that's supposed to be the candidate for. So here, n is going to be 1, and that this is going to be induced by that inclusion, by the retraction. And so let's see what's happening. We're going to, and I have some flexibility in defining this map on the spine. I have to stay within the homotopy class, but I get to choose C. So I'm looking for, say, a piecewise linear map from this graph to this graph. And that piecewise linear map, I want to have the property that this embedding energy is less than 1. Okay, so here's what I'm going to do. I'm going to send this blue edge, okay, linearly to that green edge. Okay. And you notice 2, okay, this is length 2, this is length root 2, so I have to shrink by 1 over square root of 2. Okay. I'm going to send this green edge to that red edge. Okay. This green edge has length square root of 2. That red edge has length 1. I'm going to do it linearly by square root of 2. Okay, then there's an exercise in freshman year algebra with involving square roots. I'm going to send this red edge linearly to a sub-edge of this blue edge, okay, so that the contraction factor is also square root of 2. Okay, I'm going to do that on the top, and I'm going to do it on the bottom, and it's going to miss a little bit, and it just barely fits in so that I can stick those guys in there. And when you're all said and done, you have a piecewise linear map where this embedding energy is 1 over square root of 2. And so then the theorem then implies that there's a rational-like map somehow associated to this picture, which has the right combinatorics, so that I can then cap and use QC surgery and get a critically finite rational map captured by the combinatorics of this picture. So how much time do I have?
15 minutes.
Okay, perfect. And all of this and many, many, many more details are in a 50-plus page paper by Dylan now in the archive. Okay, whoops. What happened? Okay. So what are some of the ideas in the proof? So it's kind of intuitive how to connect a Riemann surface with an elastic graph. So if you just have an edge of some length, you just thicken it to a rectangle of, say, some width epsilon. So an elastic graph determines a family of ribbon graph Riemann surfaces. Okay, you think of epsilon as the width. Okay, they won't be conformally equivalent. Different choices of epsilon will give you different Riemann surfaces, but you get a whole family of Riemann surfaces. Just if you go back to this picture, just think now of this as like, this blue thing is actually a rectangle of length 2 and then width some epsilon, and the green thing is width root 2 or length root 2 and width some epsilon, and you can join them together at the vertices in the standard way you see a simple zero of a quadratic differential. Okay? That tells you how to glue the rectangles together. It'll be some number epsilon. Okay. Okay. Then the next step is to relate extremal lengths on graphs to extremal length on these kind of ribbon surfaces. So there are some theorems in there that say if epsilon is small enough, then the extremal lengths will be comparable to each other. But what we need is a characterization of conformal embeddings. So here's a question in complex analysis. Okay? Given two Riemann surfaces and a homotopy class of embedding, phi from U into V, when is there a holomorphic embedding in this homotopy class? So this has nothing to do with dynamics or anything. It's just a question about including one Riemann surface into another. And I should say that this type of question is studied extensively in the PhD thesis of Maxime Fortier-Bourque, who is a student of Jeremy's. So here is a necessary and sufficient condition, which is new, for when this is the case. So there will exist such a conformal embedding if and only if a quantity called the stretch factor of this homotopy class is less or equal to 1. And here's what you do. On the source, you have a planar Riemann surface. You pick a multicurve, it has an extremal length on the source. Okay? So that's the numerator. Okay? And I think, did I get this fraction? Maybe source over target. And then when you move this multicurve over to the target, that multicurve, well, some elements might become parallel, but there's an associated multicurve on the target. Okay? We call that phi of gamma. And it will have an extremal length. Yeah, I'm used to thinking about modulus. Did I get it backwards? Okay.
So could you just think of an annulus?
Okay.
Annulus.
Okay. Well, I didn't say, yeah, okay. So I guess I got my fraction wrong. It should be numerator over denominator. Numerator over denominator. So if this quantity is less than or equal to 1, then there's a conformal embedding. And if it's strictly less than 1, there's a conformal embedding with, say, compact closure. Okay. Okay. So I've only sketched many of the details. This is a very long story. There are many more ingredients necessary to connect this part of the story with the proof for the new positive criterion. A number of those ideas grew out with discussions, I think, with Jeremy. I think we're at the stage where we can compute things. We can write computer programs to do things. Dylan is trying to write computer programs to compute stretch factors associated to taking pre-images under these branch coverings. I think we're really at a turning point. There's so many interesting questions, so many things to be done, connected with so many other areas of mathematics that I'm very excited to be here talking about this at this time. And not wanting to stand between you and lunch, I think this is a good time to stop.
Any questions? Isn't that theorem requiring that the critical points be periodic?
No. But it has to be hyperbolic type. So each critical point must fall into a cycle containing.
It contains a critical.
Yes.
Question? If not, let's thank Kevin again.